Okay, let's just jump right into one of the biggest questions you can ask. What is empty space? I mean, really. Imagine you have a box, and you pull out every single thing inside it. Every atom, every particle, all the light, everything. What's left? Is it nothing? Is space truly empty?
Because what if that nothing is actually something? And not just any something, but maybe the most important, most mysterious, and most powerful something in the entire universe. And believe me, this isn't some philosophical thought experiment. This is where modern physics gets really, really weird.
You see, to even begin to wrap our heads around this, we have to deal with a total shift in how we see the world. For literally centuries, the classical view was just common sense, right? Empty space is, well, empty. It's a boring, passive, perfect void with absolutely zero energy. But then quantum mechanics crashed the party. And it didn't just disagree, it completely shattered that idea. In the quantum world, that empty space is actually a bubbling, chaotic sea of activity. It's dynamic, it's energetic, and it is jam-packed with potential.
So, how in the world did we go from a perfect, boring void to a wild sea of energy? Let's dig in. This brings us right to our first stop, the myth of nothingness. Okay, the whole key to breaking this myth lies in a concept called quantum field theory, or QFT. And the first thing you have to do is forget everything you learned about particles being little billiard balls. Instead, I want you to imagine that the entire universe, every single inch of it, is soaked in these invisible fundamental fields. There's an electron field, a photon field, a field for every particle. And what we call a particle, like an electron, is really just a little vibration, a little ripple in its own field.
So, if all of space is filled with these fields, what are they doing when there are no real particles around? What's happening in the quiet moments? Well, that leads us to section 2, a sea of virtual particles. The astrophysicist Joseph Silk described this beautifully. He said the quantum vacuum is like a sea where pairs of particles are constantly appearing and disappearing. But notice that super important word he uses. They're virtual particles, not real ones. So what on earth does that even mean?
Now, this is where your brain might start to melt a little bit, so stick with me. Virtual particles are these little particle-antiparticle pairs that literally borrow a tiny bit of energy from the vacuum itself to pop into existence for a split second. How is that possible? Well, it's thanks to a famous get-out-of-jail-free card in quantum mechanics, the Heisenberg uncertainty principle. It basically creates a loophole that lets them exist for an impossibly short time before they find each other, annihilate, and pay back the energy they borrowed. It's happening everywhere, all the time.
I know. This sounds totally made up, right? Like some wild sci-fi fantasy. How could we possibly prove that this quantum foam of disappearing particles is actually real? It's time to look at the evidence. Welcome to Section 3, Evidence from the Void. And this is the million-dollar question. I mean, if these things pop in and out of existence so fast that we can't grab one and look at it, how do we prove they're there at all? It's a huge problem, but it turns out physicists came up with an unbelievably clever way to see their effects. Okay, let's walk through this because it's just brilliant. It's called the Casimir effect. Imagine you take two perfectly flat, uncharged metal plates. You put them inside a vacuum, and you move them incredibly close together, like unbelievably close. Now, because that gap is so tiny, only certain types of virtual particles can pop into existence between the plates. But in the wide open space outside the plates, anything goes. All sorts of virtual particles can appear. This creates an imbalance. You've got more particles pushing on the outside of the plates than on the inside, and the result? A real, actual, measurable force that pushes the two plates together. Think about that, a physical force generated by nothing. And this is just science at its absolute best. The whole idea was predicted way back in 1948 by a Dutch physicist named Hendrik Casimir, based purely on the math of quantum theory. For almost 50 years, it was just a wild prediction on paper. But then, in the mid-90s, our technology finally got good enough to build the experiment. And guess what? They measured the force, and it matched Casimir's prediction perfectly. The ghosts in the machine were real. And the Casimir effect isn't some lonely, one-off piece of evidence. The fingerprints of the vacuum are all over the place. There's something called the Lamb shift, this tiny, weird shift in the energy of hydrogen atoms that no one could explain until they realized the atom's electron was constantly getting jostled by virtual particles. Even the simple act of an atom spitting out a photon in total darkness, that's the atom getting nudged by the vacuum itself. So, we've got it. The vacuum has energy. It has real, measurable effects. This is a fact. But, and this is a massive but, When we try to take this amazing quantum discovery and apply it to the universe as a whole, we slam face first into a brick wall. This is section 4, the ultimate cosmic mismatch. So here's the unavoidable logic. According to Einstein's general relativity, any kind of energy creates gravity by warping space-time. That's just what gravity is. So if the vacuum is just fizzing with all this energy, it should have a tremendous gravitational pull. It should be warping the heck out of the entire universe. This energy is exactly what Einstein called the cosmological constant. And right here is where physics completely breaks. On one side, you have our prediction from quantum field theory. It screams that the vacuum should be packed with an absolutely colossal amount of energy. On the other side, you have what our telescopes actually see, a universe that's expanding, driven by a vanishingly small amount of vacuum energy, what we call dark energy today. The two numbers aren't just a little off. They are catastrophically, comically, monumentally different. How different are we talking? Well, the theory is off by a factor of 10 to the power of 120. That is a 1 with 120 zeros after it. I can't even write that number out. This isn't just getting the math a little wrong. This is, and I am not exaggerating, the single worst, most wrong theoretical prediction in the entire history of physics, period. To give you a sense of just how insane this is, the legendary physicist Wolfgang Pauli did a quick calculation of this years ago, and he realized that if the vacuum energy was really as strong as the theory says it should be, the gravitational force would be so immense that the entire universe would have crushed itself into a ball so tiny it wouldn't even reach from the Earth to the moon. But here we are. So, what does it mean when our two greatest theories of the universe, quantum mechanics and general relativity, come together and produce an answer that is so spectacularly wrong? It means we have stumbled into Section 5, Physics's deepest mystery. This is the question that literally keeps physicists up at night. It's so simple to ask, but so impossible to answer right now. Why? Why this colossal mismatch? Why is the energy of space so perfectly, ridiculously fine-tuned to be almost zero when everything we know says it should be enormous? And right now, nobody knows. The search for the answer is one of the biggest drivers in physics today. Is our whole idea of quantum fields just wrong somehow? Is Einstein's theory of gravity missing a piece? Is there some undiscovered, beautiful symmetry in the universe that makes it all cancel out almost perfectly? Or, and this is a tough one to swallow, what if virtual particles, despite all the evidence, are just a clever mathematical trick and not physically real after all? So, you see, our journey into what we thought was empty space has led us straight to the biggest unsolved puzzle in all of fundamental physics. And it leaves us with this one profound final question. Is it possible that the key to understanding everything, the Big Bang, dark energy, the fate of the cosmos, is hidden away in the one place we always assumed there was nothing at all?